Well, hello everyone. Hope you are doing well. So today we're going to be looking at this essential question. How can definite integrals be used to calculate the average value of a function over a closed interval? And by average value, we're referring to the average y value of a function. So if you want to get a little introduction, I recommend checking out this Desmos activity, playing around with it a little bit, kind of get the idea of what we're talking about. You can just pause the video and go put the code in and complete that. Totally optional, but just something we would have done in class, and I think it gives a nice introduction to the concept. All right, now we're going to move on. So here is the formula for the average value of a function. So if you want to calculate the average y value of a function over any interval, first off, this function needs to be continuous on that interval. What we're going to do is we're going to calculate the definite integral from a to b of that function. Basically, we're finding the area under the curve. And then we're multiplying by 1 over b minus a. b minus a is really the width of the interval. So essentially, we're taking the area and we're dividing by the width, and that should give us the average height, which is the y value. So let's make sure you've got that formula written down somewhere in your notes. You'll have to memorize that. It's very important. So let's look at the first example. So the first example says the temperature F in degrees Fahrenheit of a cup of coffee t minutes after it is poured is given by that function f of t, which equals 72 plus 118 e to the negative 0.093 t. To the nearest degree, what is the average temperature of the coffee between t equals 0 and t equals 10 minutes? So to find the average temperature, we're going to take 1 over b minus a. Well, b minus a is going to be 10 minus 0 times the definite integral from 0 to 10 of the function, which is 72 plus 118 e to the negative 0.093 t dt. Now at times you may have to calculate some of these by hand, but this one's pretty complicated, and we're just going to do it on our calculator. So give me a moment, because I'm also typing it in, but you can practice typing it in as well on your own. So when I type in the definite integral, I get about 1488.2 approximately. But then don't forget to multiply that by 1/10 or divide by 10. And you should get, rounded to the nearest whole number, approximately 149 degrees Fahrenheit. It's really a remarkable formula. It's quite powerful. Helps us find an average of a continuous function. Now, you might be wondering why it is that we integrate the function and yet we end up with the exact same units that we started with, because f was a function in degrees Fahrenheit and we ended up with an average value that was also in degrees Fahrenheit, even after we integrated it. Shouldn't it give us like the antiderivative? Well, if we just took the integral, it would give us the antiderivative. If we just did that part, this part right here gives us some sort of antiderivative value. The units on this antiderivative, it's a little bit odd. If we just had the function in degrees Fahrenheit and we differentiated it, we would get like degrees Fahrenheit per minute. But we are anti-differentiating it, which means we actually end up with some odd function that is in degrees Fahrenheit times minutes, because we're going backwards. So that doesn't mean a whole lot to us by itself, but the units on that 1488.2 would be degrees Fahrenheit times minutes. Well, this 1/10, 1 is just a constant. 10 is 10 minutes. And so that's really 1 over minutes. So what happens is this times minute and this divide by minute cancels out, and we still get back to degrees Fahrenheit. So with the average value formula, you end up with the exact same units that you started with. All right, example 2. So back at the beginning of the school year, like the first week of school, I had you guys look at a few big problems from throughout the year. And this was one of them that some of you looked at, which is I'll just kind of zoom in on here, this chart, which kind of plots world population over the last, 12,000 years of civilization. And so my question to you at the time was, since 10,000 BCE, what has been the average human population on Earth? And what that means is, like, if you were to pick a random time anywhere along here, if you just kind of randomly picked a time, what would you expect the population to be? Now, we know the population has, taken off. This is clearly a fairly exponential growth curve right here. So what we're going to model it with is this function. So the function p of t, which is 0.00052 e to the 0.015 t plus 100 million, models the world population since 10,000 BCE, where t equals 0 represents year 0. What is the average world population between 10,000 BCE and today, 2020 CE? So to calculate that, we are going to do, we need to first figure out what A and B are. A and B. A is the year 10,000, but that's 10,000 years before year 0, so we're going to really think of that as negative 10,000. And B is this year, 2020. So we're going to do 1 over B minus A, so 2020 minus negative 10,000, times the integral from A to B, negative 10,000 to 2020, of our function, P of t dt. I'm not going to rewrite it. I'm just going to type it into my calculator. So once again, give me a moment. All right, so I did the definite integral part. I just typed this in my calculator, and now I'm going to divide by this, which is really, what is that, 12,020. And we get, at least I got, 141 million, we'll round to the nearest whole number, 603,553 to the nearest human. So that's not very much. We know the population now in the world is almost 8 billion people. But this is saying that the average human population any time in history, since 10,000 BCE, is only about 140 million people. Because as you can see on the graph, much more time was spent with fewer people on Earth than with all the large numbers of people we have on Earth nowadays.